Alright, so welcome to the 12th and last problem. This problem is going to be about uncertainty propagation, and while it doesn't come up a lot in paper 2, it may appear in paper 3, and this skill is also very useful for the data analysis section of the internal assessment. So let's just jump into the problem. The problem says the following: a block of metal which measures 8 centimeters by 10 centimeters by 3 centimeters has a mass of 1.92 kilograms. Assume that the uncertainty in each of the lengths is 0.1 centimeters and the uncertainty in the mass is 0.03 kilograms. And we're asked first to find the density of the metal sample, second to find the uncertainty of that density of the metal sample, and third to determine whether the density of zinc falls within the range of true values of the density of the block that we have here or not. So let's get to part A of the problem. Part A asks us to find the density of the metal sample, and it specifies the units. Now let's recall that density is mass divided by volume. Now we have a mass value, which is 1.92 kilograms. It's given to us. However, the volume is not directly given to us, and we're going to have to calculate that volume before getting to calculate the density. So for this, we need to detect that the statement says a block of metal, and then it gives us three lengths, length, width, and height. So we need to detect that block has the shape of a cuboid, and cuboids' volumes are calculated using the length times width times height formula. So for that volume part of the equation, we're going to have to multiply 8 times 10 times 3. So we go ahead and do that, and the units do not need to be changed, as the question is asking for that density in grams per centimeters cubed, and here we have all in centimeters. So those length values that are given to us do not need to be changed before operating with them. So we just go ahead and multiply 8 times 10 times 3, so length times width times height, and get that the volume of that block of metal, which is a cuboid, is 250 centimeters cubed. Now for the mass side for the mass variable, we have a numerical value for it that's given to us is 1.92 kilograms. However, if we look at the units that are asked for us to give our answer in, it says grams in the mass part of the density. So that those kilograms do need to be transformed into grams before calculating that density. So we'll just go ahead and multiply that 1.92 times 1,000 to get 1,920, and that would be in grams. So we now have volume in centimeters, which is what we need, and mass in grams, which is what we need. So we just go ahead and divide those two, 1,920 divided by 240, and we get 8 grams per centimeters cubed. Now notice that it is 8.0. Now here's why. Every time you do an exercise, the answer needs to be given to the least number of significant figures present in the numbers you used. So if we analyze what we have operated with, we have that 1.92 kilograms. There are 3 significant figures there. We have that 3.0 centimeters. There's 2 significant figures there. We have 10.0 centimeters. There's 3 significant figures there. And we have 8.0 centimeters, and there's 2 significant figures there. We have used all those 4 values to reach our answer. So we need to take into account the significant figures of all those 4 values in order to get the significant figures that must be present in that answer. And the least number of significant figures of our 4 values is 2. The 8.0 has 2 and 3.0 has 2. So our final answer is going to be given to 2 significant figures, and that is why it is 8.0 grams per centimeters cubed, and it is not 8 or 8.00. So that will be part A. Now let's get to part B of the problem, which asks us to find the uncertainty of the density of the metal sample. Now, it's important to note that when it asks for the uncertainty of something, it's asking for its absolute uncertainty. So the absolute uncertainty of that measurement or of that value that you calculated. Now, in order to solve this, we're going to be dividing it in 3 steps. Our first step is to find the relative uncertainty of the cube's volume. Now, recall that relative uncertainties are unitless as they are relative, and that the way to calculate them is the uncertainty of that measurement divided by the value you measured. Now, we did not have a given value for that volume. We calculated it using 3 different values and multiplying them together. So when there is a multiplication involved, in order to find the total relative uncertainty, you need to add the relative uncertainties of all the numbers that you multiplied. So we're going to have to find the relative uncertainty of the length, the relative uncertainty of the width, and the relative uncertainty of the height, and then add those together to find the total relative uncertainty of the cube's volume. So let's just go ahead and use this formula to calculate our relative uncertainties. Now, we know that in each of these length measurements that are given, the uncertainty is always 0.1 centimeters. So that uncertainty variable of the relative uncertainty equation is going to be 0.1 for all those 3 values. So we're going to have the relative uncertainty of the length be 0.1 divided by that length value, which is 8 centimeters. We're going to have the relative uncertainty of the width being 0.1, which is that uncertainty, divided by the value that is given, which is 10 centimeters. And we're going to have the relative uncertainty of the height to be 0.1, that is that uncertainty, divided by the not measured value, but the value that's given to us, which is 3. So we perform those 3 divisions, and then we add them all together, and we find that the relative uncertainty of the total volume, of the relative uncertainty of the volume, is plus minus 0.05583. Again, no units because relative uncertainties are unitless. Now, this is going to be an important part for final absolute uncertainty calculation. So that would be step 1 for solving for part B. Step 2 would be finding the relative uncertainty but of the density, which is the value that we actually calculated. So again, to find the density of that cuboid, we divided 2 values, mass and volume. And divisions and multiplications work the same way in terms of relative uncertainties, in the sense that you must add the relative uncertainties of the numbers or of the values that you manipulated to get to that result. So here in this case, as we divided mass by volume, we're going to add the relative uncertainty of the mass with the relative uncertainty of the volume that we have already calculated here. So the equation is the same. It's relative uncertainty equals uncertainty divided by the value. We already have that relative uncertainty of the volume, which is plus minus 0.05583. Now let's calculate the relative uncertainty of the mass. And so that relative uncertainty of the mass would be that uncertainty that is given to us is 0.03 divided by 1.92. However, we need to change all of that to grams, as our final density result was given in grams per centimeters cubed, because that's what is asked. So before going ahead and calculating for that, we multiply that uncertainty 0.03 kilograms times 1,000, and we get 30 grams. And we go ahead and multiply that 1.92 kilograms times 1,000, and we get 1,920 grams. We go ahead and divide that 30 grams, that uncertainty in grams, divided by the grams that the cuboid weighs, and we get that the relative uncertainty of the mass is 0.0156, again, unitless. Now we need to add those 2 values, and we would get that the relative uncertainty of the density is 0.07143. Now, again, the uncertainty value needs to have the same number of significant figures as the result. So our relative uncertainty of the density needs to have two significant figures, just like our density measurement. So that 0.07143 is going to get rounded to plus minus 0.071, as here we would have two significant figures which would match our result for the density of that metal sample. So that would be step 2, finding the relative uncertainty of the density. Now, let's go to step 3. Now that we have the relative uncertainty of density, we're able to find the absolute uncertainty of the density, which is what we actually want. Now, recall that absolute uncertainty is relative uncertainty times the measured value. So, we have that relative uncertainty of density, which we calculated here. It's 0.071. We plug that in, and we have our measured value, which we calculated in part A, which is 8.0, and we plug that in to the measured value variable. We get in the end that the absolute uncertainty of the density is 0.568. Now the significant figures are kind of left aside, and what we need to focus on is having the same degree of accuracy in our uncertainty than in our actual value, right? So we need to have the same degree of accuracy. In the density of the metal sample that we calculated, the degree of accuracy is to the 10th place of the decimal. So our absolute uncertainty cannot be 0.568, because that would be a degree of accuracy to 1,000th place. So we need to round all that to the 10th place, just like our value for the density. And we will finally get that the absolute uncertainty of that density of the metal sample is plus minus 0.6 grams per centimeters cubed, and your final answer for density would be this one right here. That will give us part B. Now part C is easier and it's simpler. So part C asks us if the density of the zinc, and is given, falls within the range of the true values of the density of the block. So we have that the density of the metal sample is 8.0 grams per centimeter cubed plus minus 0.6. We have that the density of the zinc is 7.14 grams per centimeters cubed. Now, we need to find the difference between the densities in order to be able to determine whether it falls within the range of true values given by the uncertainty. So we do that density of the metal sample, which is 8, minus the density of the zinc, which is 7.14, and we get that the difference between densities is 0.86 grams per centimeters cubed. Now, 0.86 is greater than 0.6, which is our uncertainty, and therefore the density of the zinc does not fall within the range of true values of the density of the metal block, as it exceeds the uncertainty of that density of that metal sample. So that would be part C, and that would finish this exercise and this last problem of the channel. The presentation is again linked in the description, and I hope you learned and you enjoyed the videos, and thank you again.